Okay, we're back and we're computing the MLE. Let's go back up here so we remember what we're doing. We're computing the MLE, the maximum likelihood estimate, for an exponential family. And we're assuming that it's in natural form. So this eta of theta equals theta. And this is what we have. This is the form, and we were going through this. We wrote down this is the definition of the MLE, and we got an expression for the likelihood function. We took the log, and we differentiated it to figure out what to solve for the maximum. And we got this, and we had to evaluate the derivative of log of z of theta, the log of the partition function. And so we were computing this thing that just sort of we had to compute, and it turned out that it was just equal to the expected value under the parameter theta of the jth function sj evaluated on the random variable x, where x is distributed according to our exponential family. So this is a beautiful fact. And in fact, we could write it more generally. Let's write it more generally. The gradient of log, well, if I lined all these partial derivatives up in a vector, then that would be the gradient. The gradient is just the vector of partial derivatives. And the gradient, therefore, equals the expected value, and now it's the vector of these sj's. So it's s of x, the expected value of s of x. So it's the expected sufficient statistics. Remember, we said that s was a sufficient statistic without defining what that is. But this has the beautiful property that the gradient of the log of the partition function equals the expected sufficient statistics when this is evaluated at theta. So that's beautiful. And let's plug that into our calculation above and see what happens. So let's go back here. This is minus n times the expected value under theta sj of x plus sj of d, or no, wait, sj of x, is that right? Sj of x, yeah, that's right, plus sj of d. So this is looking sort of interesting. We have sj here and here. And if we move one over to the other side, let's see what happens. So let me write that down here. So our previous computation implies that the expected value under theta of s, I'll just write the whole thing, s of x equals s of d, right? I'm just lining these up in the vector using the same sort of thing here. Okay, and what's s of d? S of d was, by definition, that was just our little shorthand for, let's see, where was that? We defined it somewhere. Oh yeah, sj of d was this, and, well, where was s of d? S of d, where did it go? I guess maybe I didn't define s of d. S of d is just the sum of the s of x's. So this is the sum, as I goes from 1 to n, of s of x of little x I. Oh wait, something's wrong here. I think I left out. Oh yes, of course, I left out the n. My goodness, I left out the n. All important n. Right. So this becomes, right, we have the expected value, the n goes with the expected value, so this is n here. And we get that the expected value, the expected sufficient statistics, equals 1 over n times the sum from 1 to n of s of xi. So this is just the sample mean, right? This is the average of the s of xi's. So this is just the sample mean. Very natural interpretation. And this is the true this is the expectation. This is the mean of xi, or of x rather. So this says that the MLE satisfies, so at least the critical point, any critical point of this distribution satisfies, and the MLE has to be a critical point. So the MLE satisfies the property that the expected sufficient, the mean of the sufficient statistics equals the sample mean. So this is satisfied for, go back up here, remind ourselves where that came from. We wanted to find the maximum of this, so we did the usual calculus thing and we set its derivative equal to 0. But that only, if you put these up and put these together in a vector, we set the gradient equal to 0. And when the gradient is equal to 0, the gradient is equal to 0 at the critical points. And any maximum is a critical point. So that means the MLE satisfies this property. So we could put theta MLE here, and it satisfies this property. Actually, let me be a little more careful here. This is true under the assumption that, let's see, that the MLE exists. So I was assuming that the MLE exists and is in this set, capital, actually in the interior, right? So the problem was, well, let me say it here, and then interior of capital theta. So right, I was assuming that it existed, and then if there's a critical point and is in the interior, because then if there's a critical point, if the MLE is in the interior, then it is a critical point. The problem is that you could have something like this where, as a function of theta, maybe the likelihood increases to a point here, but it's not actually a critical point at the maximum. So you need it to be in the interior so that the maximum occurs at a critical point. And of course it needs to exist in this set, this capital omega. So that's assuming that, but you can prove actually a little more general condition that in fact, if I remember this correctly, that this if there is a point theta that satisfies this, then, and it's in the interior, so if theta satisfies, let me call this star, and it's in the interior of capital theta, then in fact it's the MLE. And to prove that, you need to prove that in fact that it's a maximum. This would just show that it's a critical point, but in order to show that it's a maximum, you would have to take the second derivative, right? We just took the gradient and set it equal to 0. To show it's a maximum, you would have to take the Hessian, that is the matrix of second derivatives, and show that that is positive definite. And it turns out I remember roughly how to do that, and it turns out that that's not too hard to prove if you know some basic properties of positive definite matrices. So I'll leave that as an exercise if you want to prove that. And and so just briefly, the interior, what that means is that a point is in the interior if there's a ball. It's in the interior if there's a ball around that point that's contained in the set. Okay, so that's a very nice characterization of the MLE. And this is also a very nice property here, characterization of the expected value of this sufficient statistic. And now I'd like to give you a little demonstration of how these are used in a very simple case. So let's take the case of an exponential distribution, our classical example of an exponential family. And so in that case, we had p of theta of x. Everything was just one-dimensional. Theta e to the minus theta x times the indicator that x is greater or equal to 0. And here, so z of theta was just 1 over theta. S of x was just, we took it to be minus x. And let's see, what is it? Theta, right, theta, it's natural actually, because it's natural. It's in natural form because eta of theta is theta, and h is this thing. So what is this? Well, let's see. What does this tell us? So the gradient, or actually just the derivative in this case, with respect to theta of log of z that's log of z, so that's the derivative of minus theta, right? Log of that is minus log of theta, so that's minus 1 over theta. I think I did that right. Let me write that out. That's derivative log 1 over theta is minus log theta, and that's right, that's minus 1 over theta. And that, we know from this, is equal to the expected value under theta of s of x. So what's the expected value of s of x? S is just this thing, so that expected value is minus the expected value of x. And so this implies that, so we cancel the minus signs, the expectation of x of a 1 over theta. The expectation of a exponentially distributed random variable is 1 over theta. And let me check to make sure. I think that's right. Let me check my usual reference here in the back of Grimmett and Sturzacher, the nice lookup table they have there. And indeed, yes, the mean of an exponential is 1 over theta. So that was a nice little trick. We avoided, the usual process of computing the expectation. So that paid off. And now let's see if we can get the MLE for free also. So the MLE, to get the MLE, we have our sequence of points. And let's write what this means. So the MLE, so under theta, well, I'll just put theta. S of x, and this is just the same as before. That's minus the mean, which we already know is that. And that equals 1 over n times the sum I from 1 to n. And our statistic is minus x, so that's minus xi. So the minuses cancel, and we get that implies 1 over theta equals 1 over n, I from 1 to n, xi, which implies theta MLE, assuming it exists and all this stuff at least, is 1 over the sample mean, 1 over this sum from 1 to n of the xi's. So that gives us a nice characterization of the MLE, and just a really easy way to calculate the MLE for a exponential distribution.